So the first step we'll take a look at is adding a probabilistic classifier. So we'll add the naive Bayes algorithm to train a model, and then add it to our set of tricks for classification. So first, we want to train this model naive Bayes. We want to have a tokenizer, because we want to split the words into split the sentences into words, and then feed them to our model. And also, the reason why I picked naive Bayes classifier for this is because it works very well for small amounts of training data, and it's a known method that, I mean, now we use deep learning for this, but probably like for spam filtering or classifying emails and things like that, it was a very popular method at one point to do those kinds of tasks. So that's why we're using it. So we want to use a tokenizer, and we'll use the spaCy library to tokenize our sentence into different bits of words, chunks of words. You might ask, like, why do we need tokenizer? Because you can ignore that warning if you're getting that too. Why do we need a tokenizer? Because English is space separated already. Well, yes, that works. But for example, here, if you just split on spaces in question mark, will become a token itself. So spaCy will do that nicely for you. Also things like hyphens, those also are token separated. Contractions, it's actually two words, right? What if you have different language in there? That splits it out as well. What if you have spaces? Those are not individual words, so if you split on space, that'll be problematic as well. So that's why we have a tokenizer task. And it's more important for other languages that are not space separated, like Japanese and Chinese and Arabic. Okay, so we have that, and then we look up some stop words. And stop words, like I mentioned before, are these words that don't provide too much value in the language, or too much value for the model to learn. That's why we remove them. And because they appear so often in the training data, they actually end up confusing the model. We'll look later that actually we actually don't do stop word removal when we do deep learning, because those features end up providing meaning, versus here in just a probabilistic classifier, they actually hurt. Okay. So we have a small function that just tokenizing and then puts them back together into a string with the tokens. This putting them back together is like not technically important. It's just the library that we train on expects it as a form of space separated words and not like a list of words. So that's why we just put them back together. Okay, so once we have that, our tokenization function built in, we can get our x's and y's, right? That's what we need. We present our model a bunch of x's and y's, and then it tries to make predictions based on them. Look at our intents and our phrases and tokenize them, and then just return them in the form of a list. So for our model, for training, we use, it's a very simple model. So we're not like adding any other features to our model other than just a count vectorizer. So we're converting our tokens into indices. So for example, the character the gets an index of 1, the character 2 gets an index of 2, and so on, depending on how many words you have. So we just change them into words. Just our pipeline is vectorize our words and then use the naive Bayes algorithm and call fit on that. And now we can run that. Okay, so now we have a trained naive Bayes model that can do intake classification. How do we get predictions? Same way that we did the training, right? We tokenize the text first and then try to predict on it and return the answer. Okay, so now this didn't work with our previous fuzzy matching, right? But now that's supported too. So now we have another little tool in our bag of tricks that's going to help us classify intents. But a lot of the times, the naive Bayes can get things wrong, right? So I'm not sure if this is going to work, but let's see. more complicated one. Okay, so it's still doing pretty well, but you might, with your particular data set, you might run into a case where this doesn't work, or uh, it's not very sure of a particular query, and um, you would rather prefer to answer I don't know than just returning like the wrong intent. So what do we do in that case? So for that, we can actually look at the predictions of the naive Bayes, and that's what this is doing here. So we can look at all the predictions that he made. We can look at the top 3 predictions. So okay, the one with the highest probability is when it's check-in. The one with the second highest is when it's early check-in, and so on. So we can look at all of those, and we can make a threshold. And Max had mentioned this in his talk as well. You can have a threshold and say like, okay, well, if the first intent probability, if the probability of predicting the first intent is higher than a certain number than the second or third intent, then only return the correct one. Otherwise, just say I don't know. Because for us, for chatbots particularly, it's very important that we not only return like the right answer, but we're also confident about it. Because a low confident wrong answer is going to provide a worse user experience. So that's what we do here. So look at the model probabilities, sort them, look at the top 3, and if our top one, the first one, is greater than the other 2 put together, just return the correct class, in our case, the correct intent. Otherwise, just return I don't know. Very cool. So in that case, in our case, okay, it seems like that threshold is holding, which means that when it predicted this early checkout intent or early check-in intent, it made that prediction confidently. So it's very sure that this is the right one. And this threshold is some number you want to play with. It's definitely dependent on your model and your data, and you might have to update this again and again. There are other smarter ways to do this, but for this workshop, I wanted to keep it simple. For a lot of data sets, this will usually be enough. Maybe it'll be enough. But that's something you have to do with a little bit of trial and error. Okay, so we have a few tricks now. We have our exact match. We have our exact match built in. We did some. We did some partial matching, fuzzy string matching to get better. And we added a probabilistic classifier, naive based, and we added some thresholds so that it makes a confident prediction and not like the wrong one. And we also added some pre-processing tricks so that it gets closer, the input text is closer to our training data, and we can make good predictions on it. So let's put it all together. And this is like a very, very simple and fake pipeline that you probably shouldn't write if you're designing like a system. Like a bunch of if statements. Okay, try exact match, doesn't work. Try exact match with pre-processed, and so on and so on, and get a prediction. So we tried a bunch of queries, and okay, our pipeline seems to hold. It's working for the most simple cases. So at that point, are there any questions for me to take at this stage, or should I keep going?
Yes, we do have a few questions. I don't know if we should answer them now. Some of them have been answered by the community. One comment that we have, if you could kindly speak a bit slower if possible.
Okay. Right.
And
was that all? Sorry.
Yeah, I think for now, yes.
All right. Okay, so we're at this stage. We have a few set of tricks, and we have this put together, and it seems to be working well. But it's, as we know, we can fool it in a lot of different ways. If you add more words to it, because our training data set is too small, if you add a lot of unknown words, that you haven't, that our data hasn't seen, it'll fail. It's not going to make the right prediction. So now we're at a stage where, okay, how do we get even better from here? Is where we move to deep learning from this set of tricks. And so when you decide when you come to a point where you need to decide whether or not you want to move to deep learning, these are the sort of things you want to look at. Like, well, pros, definitely noticeable improvement of using neural networks over the current models. The model can scale very well. So the more data you add to the neural network and the more training data you add, the better it's going to get. So you can keep scaling that as your system grows and as you collect more data from users. This is a good point because we're reaching the limits of rule-based systems now, because we could try to conjure up a ton of other feature engineered things, like, how do you deal with negations? So how do you make predictions when the user says, I don't want to do this? And if you don't have that, without having that particular data in there, so your model somehow has to understand that the user actually doesn't want this. And in regular machine and probabilistic models, you have to engineer that feature somehow in there in the data set to know. Whereas if a neural network, if it's been trained on enough data, then it'll just know, like, okay, that's a negation that I need to negation that I need to ignore. Also, like, maybe once you move to deep learning, you can simplify the pipeline a lot. So if you have your deep learning model trained on a ton of data, particularly a pre-trained model, then you probably don't need to do as much pre-processing. It'll probably get it on the first try if it has seen that kind of process before. Similar with like typos too, right? If you add a lot of typo in your data set and train the model on it, then it'll just know how to predict the right intent with the typos built into itself, right? So you don't need to have another pre-processing step where you clean up the typos and then try to classify the intent. But some of the cons here are that you cannot see a huge gain until your data set has been cleaned up, right? Because so far we've been building our data set so that it can take care of these smaller things that bug you, like the pre-processing and all that. But now you want to change. You have to change it again back. Also, maybe for probabilistic models, you wanted to shift them, have more varied intents based on instead of having more collective ones. So what I mean by that is the check-in, check-out late one. So if you have a model that can, for example, for this one, I had the same answer for both, right? Check-in and check-out late questions. But if you want very different answers for that, or more varied ones, like what if you want, like, is check-out late different for people coming from out of state versus in state, or what if the front desk is different depending on what time you're at the lobby. Like in the morning, maybe it's in this floor, and in the evening it's somewhere else or something, or in the weekends it's like somewhere else. So there might be some like more finer grain cases where a probabilistic model won't perform as well because it's using a bag of words model where it's not looking at the order of the words. It's not looking at the stop words either and how they relate to each other. So it doesn't know a lot about the language itself, whereas the deep learning model does, and you can make those finer grained selections. And what that means is you have to clean up your data to account for those kinds of changes now. And that means making more or less intents, or grouping intents together that were like spread out before, or vice versa. And of course, infrastructure changes. So training deep learning models means using GPUs, and that means having to move your infra so that all of that can work out properly. And you can still train in a reasonable amount of time, and deploy in a reasonable amount of time, and also do inference and return your answers fast enough back to the user.